Hello. Last time we saw how we can use various relationships to measure distances to stars or star clusters. Chief among them, relations between period and luminosity for pulsating variables like Cepheids, but also fitting of the main sequence for the star clusters. These are examples of a really more general idea of distance indicator relations, so let's just recap what that really means. In general, if we can find a correlation between some distance-independent quantity, like color or temperature or stars, or period was for pulsating variables, that correlates well with something that does depend on distance, like stellar luminosity, and we can calibrate that relation, then we can see how stars in other clusters of different distances fit on that relation. So now when we compare these correlations in apparent quantities, say apparent magnitudes instead of absolute magnitudes, clusters of different distances will systematically shift from each other. From the magnitude of that shift, we can find out what the relative distance is between them. So thus, we can use these distance indicator relations as a measure of relative distance. If we can actually calibrate them in the absolute sense, then of course we can get absolute distances as well. And this is how Cepheids work. So now the question is, can we do the same thing for galaxies? And the answer is yes. The first relation that we'll consider is so-called surface brightness fluctuations. And conceptually, it's fairly simple. Suppose we're looking at some galaxies with a detector that has square pixels, like typically they do, and each of these pixels would cover a certain number of stars. Now, if we move the galaxy twice as far, then there'll be 4 times as many stars in each pixel, and that will look smoother. The mathematical reason behind this is fairly simple. For elliptical galaxies and bulges, most of the light comes from luminous red giants, and it's the fluctuations in the numbers of those red giants that will determine what's going on here. So if we have, say, stars that contribute most of the light, and their average flux is F, and the number of them in a pixel is, then the total amount of flux from that pixel will be n times F, and the variance of that will be given by the square root of the number of stars. It's a Poissonian statistics. So if we move galaxy further, the number will go as a distance square, but flux will decline as a distance square, and therefore the variance will scale with the square of the distance inversely, and square root of that, which is RMS or sigma, as the first power. This is why a galaxy that's twice as far would appear twice as smooth. So now if we actually knew what real luminosity is for an average star that corresponds to that average F, then we can determine the distance. Roughly speaking, the mean absolute magnitude m corresponding to that mean flux F is the one of the top of the red giant branch. And we can try to calibrate that using Andromeda galaxy, to which we measure distance using other techniques. Using that gives the following calibrating relationship here. Note that this is a purely empirically calibrated relationship using a galaxy to which we know the distance. However, there is likely to be some dependence on the actual coefficients of this equation, or I should say correlation, that will depend on things like the mean metallicity of stars in a given population and so on. We also have to take care of things like removing the effects of foreground extinction, presence of foreground stars in our galaxy, background galaxies behind the galaxy we're studying, and so on. Nevertheless, this is a very powerful method and can be used to measure distances out to 100 megaparsecs using Hubble Space Telescope. Here is a simulation of how that works. The 2 columns of pictures correspond to 2 galaxies, fictitious galaxies, that one of which is twice as far as the other. Top panels schematically show where the stars would be relative to the pixel grid. Now, if we average their fluxes, we can see in the grayscale images to the second row what, say, picture might look like. Now let's add more pixels, or alternatively, we can move galaxies further out, and so we see this grainy structure, which is indeed what's observed. Finally, we convolve this with atmospheric turbulence, the seeing, because we're not observing in a vacuum. Don't have to do this last step if observing with a space telescope. And the last row shows simulated images of 2 different galaxies at 2 different distances from us. Obviously, the one that's further away is much smoother. 100 megaparsecs is a good distance, but we'd like to push even further into what's called pure Hubble flow. So remember, the definition of Hubble's law is that distance is proportional to the recession velocity that's due to the expansion of the universe. However, in reality, galaxies do move. Since the time they formed, they acquired so-called peculiar velocities because of the mutual gravitational attraction. You can imagine that if there is a large concentration of mass in some direction from a galaxy, it will be accelerated towards it, and over time it will develop certain velocity. So the actual observed radial velocities of galaxies have these two components: the component that's due to the expansion of the universe, the Hubble flow, and the other one which has to do with dynamics of large-scale structure. Now typically, today, these peculiar velocities of galaxies are a few hundred kilometers per second. For example, Milky Way moves to 600 kilometers per second relative to the cosmic microwave background, which is a good physical embodiment of the co-moving coordinate grid. And galaxies do cluster. So in our case, we're a member of the local group, and that is part of a larger concentration, the local supercluster, and our entire local group is falling to it with a speed of a few hundred kilometers per second. Since these large-scale non-uniformities extend out to scales of maybe 100 megaparsecs or so, up until that scale or thereabouts, there are going to be peculiar velocity components. Going to larger scales, things pretty much average out, and if the peculiar velocity is a few hundred kilometers per second, a few thousand kilometers per second Hubble flow would make that 10%. If we go to a few tens of thousands of kilometers per second of recession velocity, then the peculiar velocities will only matter on a percent level. This is why we'd like to measure Hubble constant to distances that are considerably larger than 100 megaparsecs. And for that, we need some very luminous objects. Galaxies and supernovae are such luminous objects, and both have been used to push measurement of the Hubble constant all the way out to the Hubble flow. This is where galaxy scaling relations come in. Remember, we explained how it works at the beginning of this clip, and if we can find a quantity for galaxies that correlates with another one, the first one being distance dependent, such as luminosity, the other one being distance independent, then we can actually do the same trick as we did with Cepheids. There are two examples of such distance indicator relations for galaxies. One for spiral galaxies called the Talley-Fisher relation, and one for elliptical galaxies called the fundamental plane. Because these distance indicator relations provide a relative distance of galaxies from each other, they do have to be calibrated locally. So for example, the Talley-Fisher relation can be calibrated with distances to spirals that are known, say, from Cepheids, whereas the fundamental plane relation can be calibrated from the distances using surface brightness fluctuations, each of which, of course, has been calibrated with the lower rungs of the distance ladder. Now, one thing to note here is that we have some idea where these relations come from, but their exact physical understanding or evolution are not yet well understood. So we have to beware. We're using a tool whose origins and the way it functions are not perfectly well understood. The Talley-Fisher relation for spirals is a very useful one. It connects the luminosity of a galaxy with its maximum rotational speed. When we talk about properties of galaxies later on in class, we will address these relations in much greater detail. But for now, just take it for granted that this is indeed the case, and I'll show you the plot. The luminosities of spiral galaxies are well correlated with the rotational speeds. And the relation has power law slope of 4, namely luminosity is proportional to the 4th power of circular velocity, roughly speaking. That power varies depending on the filter that's used and so on. We can also express that in terms of magnitudes, because log of the luminosity times minus 2.5 gives the absolute magnitude, will manifest itself as the width of the observed radial line of neutral hydrogen. Because as the hydrogen atoms move in the galaxy, they're Doppler shifted this way or that, and the faster the rotation speed, more of the Doppler broadening there is. So we can establish this correlation using spiral galaxies with well-measured distances nearby, and then try to apply it to much more distant ones. In practice, the scatter of the Talley-Fisher relations is typically 10 to 20%. The very best that has been done is about 9%. And that's including all the measurement errors. So it's actually a very good correlation when done well. There are some problems. The light from spiral galaxies is affected by the extinction in them. There is lots of dust that absorbs the blue light, well, absorbs light at all wavelengths, but more so in the blue. And the fluctuations in star formation can affect the luminosity of galaxy on short time scales. So here is the actual Tully-Fisher relation for a set of galaxies nearby in 3 different filters. There is a gradual change in slope, but that's okay. Whatever we do, we can just calibrate to that slope. But also note that the scatter improves the further in the red we go, for the reasons that I just mentioned. There is less effect of the extinction and less susceptibility to fluctuations due to the very luminous young stars. The other important correlation is so-called fundamental plane. This is actually a set of bivariate correlations which connect one property of elliptical galaxies with a combination of 2 others. But it's usually shown in this form, where a distance-dependent quantity, radius determined in a certain consistent fashion, is correlated against a combination of velocity dispersion, which again is the Doppler broadening of spectroscopic lines in galaxy spectrum, and its mean surface brightness not depending on the distance, at least in Euclidean space. The observed scatter of the fundamental plane in visible bands, say, is about 10%, so it's as good as the best of Tully-Fisher. It may be even slightly lower, and actually, why is it so small is an interesting problem in of itself, which we'll come back to when we talk about properties of elliptical galaxies. Its 0 point nowadays tends to be calibrated with surface brightness fluctuations. The fundamental plane comes in another flavor, so-called dn sigma relation, where dn is the diameter of a galaxy at which its surface brightness reaches a certain value. This turns out to be a slightly oblique projection of the fundamental plane, but it basically works in the same way. Next time, we will talk about use of supernovae as a standard candle, a very popular method these days.